This video is part of an online course on algebra, and in this video we will talk more about functions. In this video, primarily we will be concerned about how functions behave on subsets of the domain and how pullbacks of functions behave on the codomain, and after that we will explore a somewhat more nuanced view of injective and surjective functions. As we have seen, injective, surjective and bijective functions are the building blocks of any function. Any function can be decomposed into composition of these functions. Therefore, it is interesting to study how these bricks are laid out in more detail. We start with the power set. Let A be a set. The power set of A, denoted P of A, is a very simple collection. It is the set of all subsets of A. In more detail, the power set of A denoted by P of A is the set of all x such that x is a subset of A. Let us see a simple example to ground our understanding. Consider a set consisting of 3 elements 1, 2, 3. Then the power set consists of the following subsets. We first have our friend the empty set. Notice that the empty set is a subset of any set, therefore, the empty set is always an element of the power set. Now, again I emphasize the empty set being an element of a set and the empty set being a subset of a set are entirely different things. The latter is always true, the empty set is always a subset of any set, whereas it is quite uncommon that the empty set is an element of the given set. That is not so commonly going to arise. So, here we go again. The first element is the empty set, then you have the singleton sets, singleton set 1, singleton set 2, singleton set 3, then we have the sets with 2 elements 1, 2, 1, 3, 2, 3, and finally we have the element or the entire set A itself, the set 1, 2, 3. Okay. As you can count, you will notice that there are exactly 8 elements in the power set of A in this case. You should think about why there are exactly 8 elements, and you should also think about what would happen if A was the set 1, 2, 3, 4 instead. How many subsets will be there for the set A in that event. Okay. Now that we have defined the power set, we can define the push forward and pull back. These are operations defined on the power sets of A and B. So, start with the function f from A to B. This induces 2 functions on the power sets P of A and P of B. These are called the push forward and the pull back, and the names are extremely self descriptive. We will see what they are. What does the push forward do? Well, it is denoted f lower star. It is a function whose domain is the power set of A and whose codomain is the power set of B. And what does it do? Well, it eats a subset x and it maps it to the set f of x as x arranges through x. So, what you do is you feed elements of capital X 1 by 1 to f, that will give you elements of capital B. Those elements you collect together in a set, call that f lower star x. Now, writing stars is all cumbersome, and as you would have noticed by now, mathematicians are extremely lazy. So, what we will do is we will just abuse notation and just write f of x. Now, technically this is incorrect because f cannot eat a collection of elements coming from the set A, it can eat only individual elements. If you give the elements in a plate, namely in the form of the set capital X, f does not know what to do with it, it can only eat directly from the bag A. However, we will abuse notation and just write f of x to mean f lower star x. Okay. The pull back, you can think of it as the dual of the push forward. It is written f upper star. It is a function from the power set of B to the power set of A. How is that defined? Well, you look at all those elements x in A that when fed to f will give elements of y. So, f's upper star y is the set of all elements in A that gets mapped into y under the action of f. So, that is f upper star y. Again we will abuse notation and we will just write f inverse y for f star y. Now, notice there is a danger here because f inverse is playing double duty. F inverse is supposed to denote the inverse function if the function f happens to be bijective, but we will still abuse notation and just call it f inverse y. To be more pedantic, we will usually read this as the pre-image of y under f. That is the more elaborate way of saying it, but we will often be just brief and lazy and just say f inverse y. Now, if you start with a single element b in the set B, we will double abuse notation and just write f inverse b to mean f inverse set with b, which in turn actually means the pullback under f of the set singleton b. So, as you can see, all this is done to simplify notation, but you should keep in mind that when you are abusing notation, you should not get confused. The set f inverse b is also called the fiber over b. So, this terminology of fibers you will understand better as you learn more advanced courses, but this serves as a convenient shortcut. We can often refer to the set f inverse b using words. We will just say fiber over b. Now, there are several identities that involve these push forwards and pullbacks, and I am going to summarize the most important ones here. I will not be proving all of them because the proofs are rather tedious and straightforward. Again, by tedious I do not mean they are difficult, they are just boring. You just have to keep proving two sets are equal, which essentially means start with one element on the right set, then proceed and show that that element is there on the left set, then start with an element on the left set, show that it is there also there on the right set. It is extremely boring and not very instructive. So, let me just state these results and just prove one or two just for sample, and you can do the rest yourselves. Now, I emphasize that these identities should become second nature to you, because as you progress in your mathematical adventures, you will realize that many times such identities are going to save the day. In a complicated situation, sometimes these identities can really help you out. They occur so commonly that nobody really bothers to even think twice when you are applying these identities. Okay. Start with a function x to y and take sets A subset of x and an indexed collection of sets ai. Please recall what this means, and b comma bi be the corresponding ones in y. Again, I comes from an indexing set capital I. The first thing says, if you push forward A, then pull it back again, then you might get a set that is larger than A. So, A is a subset of f inverse f of A, and equality occurs if f is injective. If f happens to be injective, A is equal to f inverse f of A. Analogously, if you first pull back the set B, then push it forward under f, you will be inside B again. You will not go outside B, but you might not exhaust the whole of B. You will exhaust the whole of B when f is surjective. If A1 is a subset of A2, then f of A1 is a subset of f of A2, and an analogous statement holds for pre-images. This one is the most straightforward one, so I will not prove that at all. And you have another straightforward identity, f of A1 union A2 is just f of A1 union f of A2. This is almost obvious. In fact, the same thing is equally obvious for arbitrary unions. F of the union of the sets ai equals union of the sets f of ai. Then you have this property of intersections. F of A1 intersection A2 is a subset of f of A1 intersection f of A2 with equality if f is injective, and a similar statement holds for arbitrary intersection. Finally, we are getting to the end of this boring slide. The pullback of B1 union B2, the pre-image under f of B1 union B2 is exactly equal to f inverse B1 union f inverse B2, and an analogous identity holds for arbitrary unions as well as arbitrary intersections. So, I am going to leave it to you to formulate. I have left several formulations itself for you. I leave it to you to formulate and check the proofs. Let me just prove two of them for fun. I will prove the first and last identities. The other proofs, as I said, are extremely similar. Okay. Start with an element x in A, then by very definition we have f of x is an element of f of A. That means when you pull back f of A, that means you are going to collect all those elements that get mapped into f of A. That is the definition of the pullback. Certainly A is going to be there, because by definition if you take an element in A, it is going to land inside f of A. So, that takes care of the fact that A is subset of f inverse f of A. If f is injective and you have an element x in f inverse f of A, then by definition f of x is there in f of A, which means x must be in A. Why is that the case? Well, if f of x is in f of A, then there is some element, let us say little a in A, such that f of A equals f of x. Then by injectivity A has to be equal to x. So, I have swallowed a step or two here, because otherwise it is going to get really boring, but I hope you understand the basic logic. It is just chasing the elements as you travel back and forth between A and B. Thus, f inverse f of A is a subset of A and we have equality. Now, for the last identity, suppose x is in f inverse B1 union B2, that means f of x is there in B1 union B2. That is what the definition means. The set of points in f inverse B1 union B2 are precisely those points that are mapped by f to the set B1 union B2, which means f of x must be in B1 or f of x must be in B2, which means x must either be in the pullback of B1 or the pullback of B2, and hence x must be there in the union of the pullbacks. Thus, f inverse B1 union B2 is a subset of f inverse B1 union f inverse B2. The other inclusion is exactly similar. You can just work it out. It is just going to take you a minute or two. So, I have proved two identities. Please work out the others. It is very good practice, and it will also make the identity stick in your memory, so that you can use it whenever the opportunity arises. Now, on to this more nuanced view of injective and surjective functions. So, the starting point is this: suppose f is a bijective function. Now, what does this mean in more glorious detail? Well, a function after all is just a subset of the Cartesian product. So, what we call a function f is in reality a set. And how is this set going to look like? It is going to look like ordered pairs a comma b, where a and b, a comes from a, b comes from b, and this is not going to be all our ordered pairs, only some of them. I have just suppressed the the way I have written it looks like I have written the definition of a cross b. All I want to say is f is going to be some collection of a comma b's. Now, notice that this can be properly also called the graph of f. Why do I say this is the graph of f? Well, way back in 8th standard or 9th standard, you had to do this tedious exercise of plotting straight lines and parabolas and what not, various curves on graph paper. You will be given a function. What do? You sample certain values in the domain. So, you draw this axis, you sample various points in the domain, look at where it lands, that will give you a bunch of points, and then you just draw them together and say that is the graph. So, essentially when you are graphing the function, you are just plotting these a comma b's in the graph paper. So, you can rightly think of the modern viewpoint of function is that a function is identified with its graph. Okay. With that preliminary done, what is the inverse of a bijective function? Well, if you think about it, you just flip the graph. What do I mean by that? Well, f inverse is nothing but b comma a such that b comes from b, a comes from a. Again, I emphasize I am not trying to define the Cartesian product b cross a. I am just saying it is going to be a collection of some ordered pairs reversed b comma a. Okay. So, the existence of inverse is essentially, the inverse is essentially obtained by just flipping over the graph, just swapping the elements. Now, what I want to do is, I want to show that injective functions and surjective functions almost have the same property. What do I mean by this? Well, we say a function f from a to b as a left inverse if there is a function g from b to a such that g composed with f is the identity on a. That is, you start from the set A, via f you travel to b, then via g you travel back to a. Then you would not have travelled at all, you will be where you started off with. That is what g composed with f equal to identity A says. We say f as a right inverse if there is a function h from b to a such that f composed with h equal to identity of b. Exactly similar definition, except now you start using h, then travel back to b using f. Okay. A function f has a left inverse if and only if f is injective. A function f has a right inverse if and only if f is surjective. A function f has a two-sided inverse if and only if f is bijective. So, this is a somewhat more subtle viewpoint, a subtle way of looking at injective and surjective functions. So, what I am going to do now is I am going to show just one of these properties. I will show that a function f has a left inverse if and only if f is injective, and I will leave you to figure out all the other parts. They are all extremely similar, but I cannot emphasize how important it is that you work it out on your own, so that you get an idea of how such things are done. So, what happens many times is you see others working out proofs and you think that it is equally easy for yourself to do the same thing, but it is not true that proving is the same skill as understanding a proof. Understanding a proof is substantially more complicated than proving, understanding a proof is substantially easier than proving it on your own. Okay. So, we will now show that f is injective if and only if f has a left inverse. So, what do we have to do for that? So, let us suppose that g from b to a is such that g composed with f is identity on a. Then we have to show that f is injective. How do we do that? Well, suppose f of x equals f of y, then g composed with f of x equals g composed f of y, but g composed with f is just identity. So, this is simultaneously equal to x, which is simultaneously equal to y. In other words, that means x is equal to y. So, this shows that if you have a left inverse, then f has got to be injective. On the other hand, suppose f is injective, suppose f is injective, then we need to define a function g from B to A such that G composed with F is identity on A. Okay. So, how do you do that? Well, let us think about this for a second. Suppose you have an element x in A that gets mapped to the element f of x in B, right. So, you want G composed with f of x to be x again. So, it is natural to say you define G in two pieces. You define G of y equals f of x, sorry, equals x if f of x equals y. So, what you do is you first define g of y to be x if f of x equal to y. This is defined only when y is in f of a. If y is in f of a, this definition makes sense because for y there will be exactly one x such that f of x equal to y. Why will there be exactly one x? Because of injectivity. Now, what do you do if y is not in f of a? Well, you choose your favorite element a in A, choose some element a in A and then just define g of y to be A. So, g is defined in two pieces. On the piece that is there in the image of f, you just map it back to where it came from. If it is not in the image of f, just map it to some fixed element. Now, you can clearly check that G composed with f is the identity map. In an entirely similar way, you can show the other things, that existence of right inverse if and only if f is surjective, and existence of two-sided inverse if and only if f is both surjective and injective, namely if f is a bijective map. So, this concludes our study of functions. Of course, this does not mean that we will never encounter a function again. The rest of the course will be about functions. You will encounter a lot of functions. What I mean is, this concludes our general theory of functions. So, from the next week onwards, we will be studying about binary operations and groups and other algebraic structures. In that context, the functions that we will be considering are what are called homomorphisms and isomorphisms. We will briefly introduce those notions in this course, and in Algebra 2 and Algebra 3, we will study homomorphisms and isomorphisms extensively. So, that concludes this video. This is a course on algebra and you have just watched the video More Functions.